Here we are, finally in the course, something new. You might say to yourself, oh gosh, these questions are all new and different. They're all really just harder. Everything we've done up to this point is just a harder example of what we did in grade 11. But circular motion, it's new, it's different. It's one of the few, I think, things that are actually not just an extension. We learn momentum later on, that's new. Electric fields, that's new for sure. Magnetic fields is new. But this is the first time in the course that we do something that's genuinely new. That I think that I would think that if you're really good at physics, I probably could have easily not explained one thing to you up to this point in the course, and you would have been able to apply your grade 11 knowledge to figure it out if you're really sort of keen and ready to try it. But this time, this is new, okay? And circular motion. So. When I say UCM, uniform circular motion, it means something's moving at a constant speed in a circle, okay? But when something's moving in a circle, it is constantly accelerating because it's constantly changing direction, right? So one of the most important things to get and to understand about circular motion is what force causes the acceleration, okay? Because if you understand that, then you can calculate it's called centripetal force. You can calculate anything you want about circular motion. So let's just look at the Earth orbiting the Sun, and understanding the force and the direction. And I think probably you could take a guess, and I'll just write it down right here. The force that causes the Earth to orbit the Sun is gravity. The direction of that force is and if you look at the little animation, it's hard to say the direction because it is constantly changing. Similar to the acceleration, it's constantly changing. But the one thing that doesn't change is it's towards the center of the circle. Center of the sun in this case. But that's the hint. It's always centripetal force, or the force causing circular motion is always towards the center of the circle. Okay? Another example, which is, this is me swirling my keys on my lanyard. Here's my husky lanyard and my keys at the end. And again, I spin them in a circle, okay? And imagine in this case I'm spinning them clockwise, so coming around, right, in this way. So what force causes them to move? Now, if you think about it, you might want to say, well, my hand or something like that, and that's true. But if you think about the keys specifically, what's causing the keys to move, it'd be the tension in my lanyard. And then I cause that tension by the force in my hand, right? But the force causing the motion of the keys themselves is tension, okay? We've talked a little bit of tension. And then the direction, just take a guess. The direction is always towards the center of my circle, okay? And just to give a clear example, when I'm at the bottom, the tension in this lanyard is up, holding the keys up. When I'm at the top, the tension is down. Now there is another force at the top because there's gravity as well, right? Pulling straight down. But here, the tension in this lanyard is towards my hand, etc. What's this? This is going to be, oh, you can read that. It should be in your notes. It just kind of made me laugh because physics questions are dumb sometimes. Okay, so here's Napoleon playing tetherball, and if I haven't showed you the SciShow video on this yet, then I will soon. But what force is causing, so he pushes on the tetherball, and what force causes the motion? And once again, anytime it's a rope or something like that, it's tension, and I bet you can guess the direction of that force. Actually, the direction of the force is actually on an angle, isn't it? Because the string, actually that actually looks like there is no string, which is kind of cool too. But we know the string on a tetherball kind of goes this way. But what's causing it to spin in the circle isn't the downward component of that. It's the horizontal component. So it's the tension, and I could be more specific and say horizontal component, but I don't want to confuse the situation. Like, we're not going to calculate when we deal with circular motion. We don't do much with direction components. I don't think. I might be lying to you, but it is tension causing it to move, okay? It's causing it to circle. Oh, duh, towards the center. So it is upward as well, but that upward part of the force is just keeping it from falling to the ground. It's the horizontal part of the force that causes it to move in a circle. Okay. So the force that we concern ourselves with in this course, in this part of, I forget the course, in physics with circular motion is called centripetal force. And the thing with centripetal force, it has an equation, which is nice, but it always has usually two equations because there's two ways of finding centripetal force. Centripetal force is the circular motion force, but it's always a kind of force. So, you know, I know you're probably writing right now, but if you could just stop writing for a second. If I'm talking about gravity, for example, my centripetal force is the gravity force. It also has this formula right here, and that's what makes us be able to calculate stuff with circular motion, okay? So the details, you know, circular motion is a F with a little c, centripetal force, sorry. So centripetal means center seeking, okay? And so there's always a force towards the center of the circle, and that's what causes the motion. The direction towards is, both of these things are true. It's perpendicular to the motion, which also means towards the center of the circle, okay? And if I could just, hold on, I'm gonna move. I'm gonna switch slides here, just looking at the best example, I think, is the gravity one. Sorry. So here we got, at any point in time, the direction of the force, my motion is like, if I'm at the very top, for an instant, the motion is directly this way, sort of tangential to my circle, while the force is directly towards the center. They're at right angles to each other. And that's always the truth with centripetal force. Okay? So you can finish writing that, pause it. Yeah, and then there's AC, like what's that? It's another thing we have to learn, but it's centripetal acceleration. Okay, and we'll talk about that next. Anyways, pause it if you need to finish. I'm moving on. So AC is the resulting acceleration caused by circular motion. And it has a nice, easy formula. It's a speed squared, not velocity, speed squared divided by radius. Can't do velocity because the velocity always changes. Okay? So two terms that we used last year that I want to make sure you can use, because sometimes we use this. We also sometimes use period and frequency. We have two more formulas. So period is the time for an object to complete a full cycle, so in one full revolution on our circle. So we use that term a lot because we have an equation we can use it with. We give it the symbol capital T, and it has units S. I know T can be temperature, T can be lots of things. I like to be T to be tension too, but I don't usually do it anymore because I don't want to confuse all the T's. But tension is, so it is 1 over frequency. It's the reciprocal of frequency, and it is the time for a full cycle. Frequency is just the number of cycles in 1 second. So it's just 1 over T. And we give it symbol, usually hertz is the unit. Sometimes we say seconds to the -1 because it's 1 divided by seconds. Okay, so those are the two more terms besides centripetal acceleration. And the reason I'm doing this, jumping to these two things right now, is because there's two more formulas for centripetal acceleration that use, one uses tension, or sorry, one uses period, and one uses frequency. Yeah, not on this page. So again, pause if you need to. So looking at my alternate equations, I use the idea that speed is distance over time. So the one formula I know is that, I'm jumping back here, is that this. So given this to be true, I'm going to get another equation in terms of period and another one in terms of frequency. And the reason is, it's AC equals V squared over R, right? Well, V, like if you say the distance around a circle is 2 pi r, that's the circumference, and then the time for a full revolution is T, is period, right? So V would be distance, that's the distance, and that's time. And I want to square it, then this is what it is. Right? So then I can say, going back to this formula, if I write, this, this bit here, instead of V squared, I have another formula that has nothing to do with V. So if in a given question or in a lab that you do, for example, you measure period, you don't usually measure the speed of circular motion, you measure period. Your lab in this unit is, in my opinion, awesome. It's hard, but it's pretty awesome. But you won't measure speed, you'll measure period. You'll measure how long it takes to do a full revolution. So this is the formula, that useful formula. And then the third form of the formula, so this is the first, this is the second, and the third form of the formula is just, instead of writing T, write 1 over F, and you end up with this. Okay? So those are the 3 formulas for centripetal acceleration. Okay? We can use those formulas in simple examples here. I find these to be pretty simple. Sorry, this is just looking for centripetal acceleration, given that, sorry about that, we know a radius and we know the speed. Just use the formula, right? That's all this is. Nice and easy. Okay? You can pause to write that out. I'm just going to jump to the next one. There we go. Sorry, this is another one where this does this to me. Okay, so a salad spinner with a radius of 9.7 centimeters rotates clockwise with a frequency of 12 hertz. Say at a given instant the lettuce is moving west. So you're looking down on it, it's moving west. So we want to first find the centripetal acceleration, and then we want to find at that particular instant when the motion is west, what's the direction of the force or acceleration. Force and acceleration will be the same direction. So we know the radius, we know the frequency, we solve for AC, very simple. Magnitude is just the number, okay? Now just looking at, so once you've got that, that's just simple. These are nice and easy, sub and solve. No, you don't have to think too much. The direction's interesting. If I say, there's north, I'm looking down on my salad spinner, and it's moving clockwise, okay? It's moving west at this particular instant. Then my force has to be perpendicular to me towards the center of my circle. It's going to be up, okay? Not up, north. So I'm saying I'm looking down on it. Okay, so this is me looking down on my salad spinner. I know that it's moving clockwise, so therefore when it's moving west, okay, because if it doesn't move west here, it moves west at the bottom. So anyways, that's just, they're pretty simple examples with centripetal acceleration. Might even have one more easy one. Yeah, last one. So this is an electric fan blade. Yep. And I know there's my acceleration, and I know the radius, the distance between the tip of the fan blade and the center, so that's my R. Calculate frequency and period. So here it's just, rearranging the formulas, okay? And then once you have frequency, you just rearrange it for period. So this is just the AC formula rearranged. I might have one more example. Yep. Okay, here I got a bug sitting on a DVD. Okay, the DVD is spinning so that the bug moves around its circular path 3 times per second. That sounds like frequency to me, right? Calculate, excuse me, calculate, I want centripetal acceleration of the bug and the net force on the bug. Also, identify the force or forces responsible for the centripetal force. So this bug is sitting on a DVD. It's horizontal, right? It says it's horizontal. And it's moving around in a quick circle. So first of all, here's all the information I have. I know the mass of the bug, I know the radius, I know the frequency. 3 times per second is the same as 3 hertz, but I chose to rotate it as 3 seconds to -1. It's the same thing, okay? And I need these 2 things. So first of all, just applying AC formula. Solve for AC, given the radius and the frequency. So I know my centripetal acceleration. And then net force is just the centripetal force, okay? So it's mass of the bug times the centripetal acceleration. So that's pretty easy. And oh, by the way, those are good answers. I'm going to check mark them because they're good ones. Now, identify the force responsible for the centripetal force. We'll talk about it tomorrow. But think about it. What's keeping that bug? What's keeping the bug on the DVD? Why isn't he flying off? We'll talk about it tomorrow. Okay. Last little bit that I want to talk about. This is a long note. But why is it when you travel on a curved highway in circular motion, you feel pushed into the door? Okay? Or, why is it that when you're on the Graviton, you've been on this ride here. I think I purposely put a little video on. If there's another. Come on. I'll have to watch that.
Welcome to another edition of I Don't...
We'll watch that in class. Don't worry about that. But when you're on the Graviton ride, why is it that you get sucked to the outside? Okay? And you're probably saying to yourself, centrifugal force. Here's the thing about centrifugal force. Centrifugal force, it's made up. It's not a real thing. It's kind of like normal force. It's just used to explain something. Okay? Because if you didn't have your centripetal, your center-seeking force, if you're moving in a circle, if it disappeared quickly, you just fly off on a tangent. And this is an example of literally flying off on a tangent. So we use centrifugal force to explain inertial effects of circular motion, which means that, inertia, like when you're turning a corner, for example, on the highway, you're kind of, you feel yourself pushed into the outside door, right? And that's because your body's still, your car's turning, but you haven't, there's no force that's caused you to turn until you run into the door. Well, there's the friction between your butt and the seat, but, your arm sort of runs into the door because your arm's still going straight, and the door pushes you around the corner, right? So we think, it feels like things are flying to the outside, but they're not flying to the outside. It's just that they don't want to turn, any object spinning in a circle kind of wants to go straight. That's inertia. But it can't go straight because it runs into something, right? Or, if it's a salad in a salad spinner, right? And it's spinning around and it's the wall in the salad spinner keeping it from flying off on an angle. In the video I'm going to show you the tether ball. It's the tension in the rope. Otherwise it would just fly off straight. If the sun disappeared, the earth would fly off on a tangent, right? Right away, or 8 minutes later it would, because gravity follows the length of time that light travels. First experience it, but 8 minutes after the sun disappeared, the earth would just fly off on a tangent because there'd be no force holding it on its circle anymore. And the direction that it would move is exactly the same as the direction it's moving the instant the gravity disappeared. Anyway, so that's what centrifugal force is. That was a really, really long lesson, longest one probably of the year, but this is the first new one we've really done. And tomorrow you'll see some more examples.